Okay, so today is the final lecture of 3031, and I have some important announcements for you. The first one is about the assignment. The deadline is next Wednesday, and the solutions will be posted one day after the deadline. Okay, so it will not be easy for the TA to finish marking before your final exam. Okay, so everything is electronic, so you can compare with the model answers. And we have exercise class this week. So today is the final lecture, but you still have a little bit of work to do before the end of the term. And this is for completeness. TA will discuss this T dependence of chemical potential, which is something I mentioned in the class. Okay, it's about that Fermi-Dirac distribution, that figure I show in the class. And then I mentioned that mu has to take some temperature dependence, but how do you really show that? It's not that easy. It's rather messy, but it's manageable for you. Okay, and the final exam will be held on the 5th of May. Rather late, 5:30 to 7:30. So I encourage you to eat well before you come. And the venue is shown here in Chongqing College Multipurpose Hall. And always check RES website for the time and venue in case they change it. Very unlikely, but possible. And you are, if you are unable to attend the face-to-face exam, you need to let me know. Don't type here in the chat. That is difficult for me. I might not be able to access this information later. So I need I need an email from your CUHK account to my CUHK account, so we can assess all this application case by case. And the result, actually, there's one announcement this morning. Everything is mentioned there. So go and check my announcement sent to everybody today. Okay, the coverage will be from lecture 1 to the final lecture. I can say a little bit more than that. Okay, this is official coverage. You will have to still worry about thermodynamics. Okay, it's not, we already had the midterm on thermodynamics. So don't assume those parts will not be there. So there will be a little bit less thermodynamics, but not too much less. Okay, so I would say roughly half on thermodynamics, the other half on statistical physics. But after all, this is related. So be prepared to see some questions that has a mixed flavor. Okay, that's all for all these announcements. And obviously, the other important issue is bring your own stationary calculator. And this is, it will be a RES event. So I will be there for the first half an hour, but I think if you forget your calculator, they will lend you, but they might not be too happy if everybody wants to borrow calculators. Okay. All right. Any quick question about this announcement? If you have something, just raise your hand. I will wait for your question. Okay, are you with me? If you have no question, also say no. So I will move on. Okay. Thank you. Last lecture, we talked about phonon. So somebody asked me to give some visualization of phonons. As I say, if I have more time, suppose this is a solid state physics course, I would do it differently. So I cannot really do much, but I will show you this. Okay, do you see something moving on your screen? Yes, 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 yes. Okay, good. Now, so these will be the key examples of lattice wave that you can expect to get if you solve this problem in solid state physics. Okay, so just very briefly, these circles, these blue circles are the atoms. Okay, and these atoms are displacing from the equilibrium position. So the equilibrium position, we will draw a straight line without any displacement. So you see this displacement, and this is the normal mode of the problem. That is to say, all these atoms are having the same frequency omega. Okay, so what you want to now the wavelength I talked about last time, I told you there's a maximum wavelength. Sorry, there's a minimum wavelength, and that you should imagine taking a camera and take a snapshot at an appropriate moment. For example, when they line up, you cannot identify the wavelength. You'll be very unlucky to take that picture. So if you take a picture, take a snapshot, that is to say you set the time to some specific value, that is the wavelength I'm talking about. So this is a chain of atoms lining up in real space. Okay, and therefore you can see this kind of wave is not the same as a mathematical wave that you will create by Mathematica or by MATLAB. You plot some sine function, right? So that is this picture I drew. So sorry if you couldn't get this point here, right? So these atoms are displacing like what I showed in this animation. So if I ask you to create a lattice wave with this kind of pattern, this orange color, you cannot do that because you don't have enough resolution to create this wave. Okay, and therefore, as far as the lattice wave is concerned, there is a minimum wavelength, and that is why if you reverse all these steps, there is a cutoff frequency. Now, I'm not saying that this is the maximum omega, but this is proportional to the maximum omega. Okay, is it okay? The student who asked this question, I don't know whether you're here. Okay, so maybe you can look at, you can just Google. There are tons of animation out there. This is the this is quite different from this. Okay, so this is the long wavelength limit. You can see if I take a snapshot, the wave will be like this, right? Okay, so my cursor is wiggling very fast, but this one, the wavelength is very, very long. Okay, this is like the sound wave you will have in solid. Okay, so this is a long wavelength limit, or what we call the 0K limit. Okay, so what should we do today? What we should do today is to continue this discussion and get the heat capacity, the T-cube law. What did we do last time? I told you that you have this kind of omega versus K. This is called the dispersion relation. And this dispersion relation, we are going to approximate that as just 3 branches with the same sound velocity, and that is why I drew it like this. Okay, so this is a 3-fold degenerate, and that's why you have a multiplicity of 3 here. Okay, for this is a very clear cut here. Actually, I like this figure. For each K here, you will have 3 different omega values, and that is why for each K here you will have 3 omega value, because you have this multiplicity you need to consider. Okay, so this is threefold degenerate. And this is all related to this cutoff argument. And the different way to argue about this is for a solid with one atom in the unit cell, we will have 3n normal modes in 3 dimensions. Okay, so all this, this is the 1D picture. Is if I allowed all these atoms to displace along all 3 directions, I will have this integral to solve, and therefore this omega d cannot be infinite. So that was the beginning of that cutoff argument. Okay, this is one viewpoint, and the second viewpoint was related to the fact that there's a minimum wavelength. Okay, so if you solve this equation, you already know g of omega d omega, which is this expression here. You plug it in and integrate, you get this result. And this result will be useful for us to simplify some other integral later. Okay, so let's do that. What do I want? What I want is to get the total internal energy. So this is the total internal energy we are after. And how do you do that? You should, by now, you should be able to just write it down without thinking too much. So what we need to integrate? We need to integrate the energy times the number, right? Just like you sum epsilon sub I n sub I. So how many particles are in that particular energy level. So when you integrate, you do something very similar. You integrate the energy. What is the energy in this case? The energy in this case is h bar omega. And what is the number? This is in the continuum limit. So I have n omega d omega. Okay. Always remember the origin of this. You will be using so much this equation so much in later courses. You might forget the reason. Okay, so this is very similar to the case of photons. That's why we put it here. The difference, the key difference here is this omega d. Okay, so you have this omega d as the upper limit. Okay, so the rest is just copy down the equations carefully. So it's not long. Let me write. This is omega d, h bar omega. There's a h bar omega here, and this one is g of omega d omega times the appropriate statistics, right? So that is the Bose-Einstein distribution with the chemical potential set to 0. Okay, so that is the source of all this. Okay, so I already know g omega d omega, so I would just write it down. So this is 3v times h bar 2 pi square, and the speed of sound to the power of 3. Okay, and then I have this famous omega square dependence for g of omega, right? So I have omega square there, and I have one more omega here. So altogether I have 3 omega multiplied together. And then this is the statistics I need to use. I need to use e to the energy minus mu. Mu is 0. Okay, and then minus 1. This is the full equation. Okay, and then you see this kind of factor here. This can be simplified. Why do I ask you to remember this? Because I want to simplify things. So I simplify using this expression. So I will mark it for you. I will mark something like this for you. So see this expression. So once you do it properly, you get this. h bar omega cube. Okay. Now, depending on what you want to do with this the statistical phonon, you can calculate all kinds of things from here. Now you get very concrete prediction. So what I want is heat capacity. So I will just take the derivative of U. Okay, this is actually constant volume because of the ensemble we use. I will just write it like this, and you will have 9n omega d cube. Okay, and then the derivative will enter here, and you will see nothing but this term here. So the t dependence is hiding here, which is annoying because it will give a very messy formula. But it's messy. It's not difficult, but messy. Okay, I will give you the expression h bar omega to the power 4, and then you have this exponential of h bar omega kbt, and then you have this whole thing square. So e exponential of h bar divided by kbt, this whole thing minus 1 squared. Okay, and don't forget you have to differentiate this argument again, so you get kbt squared. Okay, and simplify it. You see, you have the key here is to realize later I want to let this ratio, this dimensionless quantity, to be x. Okay, so you want to simplify it properly to make sure you can do that. Okay, so this is the principle behind this, and in the end you will get this result. So you get 9n kb. This is promising already. If you do it properly, you get this ratio, right? You know you need something like this from your Toulon Petit. You have n times kb, so this is a good unit to have. Okay, so then you have T divided by Debye temperature cube, and then you have this Debye temperature divided by T, and then this is x to the 4th, e to the x, and then you have ex minus 1 square. Okay, so let's write a few more words. So as I say, what is x here? It shouldn't be surprising for you at the end of this course that we always like to do things like this. We let x to be the ratio of the energy scale. We did it so many times. We did it for phonon. We are doing this for phonon. We did this for photons. We did it back when we discussed Fermi gas, and even further back when we discussed the magnetic field energy scale, and in relation to the thermal energy scale. You have mu bb divided by kbt. Okay, so this is this guy here, x. What is x? X is this. And what is this theta d? Again, this is the different way to write energy scale. So this theta, you see theta goes with t, right? So this is what we call the Debye temperature. So theta d, this is the Debye temperature. This is because I probably don't like to use frequency as the energy scale. It's hard for some people to imagine, right? H bar omega d, give you the omega d and ask you to imagine this temperature scale. Not easy, so we will convert to temperature scale. It's just a way for us to get some feeling. Okay, so this is the Dubai temperature here. And then we did it once a long time ago when we talk about the Einstein temperature. And go back and look at that. You will see a lot of very similar treatment here. Okay, so maybe I want to say one more word. It's a good chance to do this. Now, here, there's a way to actually unify this Einstein treatment of heat capacity with the Debye treatment of heat capacity. So Einstein way of doing this is basically assuming this omega is a constant. Okay, so let me draw it here. So this is the Debye way of doing things. So Einstein, we didn't do it this way, but if you want to use this kind of formalism, you can think of Einstein as having a frequency which is flat. So this is the Einstein frequency. Okay, so here, another way to say that is the Einstein dispersion is flat. So the Einstein frequency is K independent, whereas the Debye, in the Debye model, omega is linearly proportional to K, at least at the long wavelength limit. Okay, so this is one way to look at this picture. Okay, where are we here? This is where we are. Okay, so we have this expression here. This expression here contains everything you need. My Debye TQ law is actually in front of you, if you know how to extract this. So let me do it now. Okay, so we get this result. We want to learn more about this. First, you want to make sure you have done something correct. You have done something right. So how do you check? So the way to check is to evaluate the high temperature limit, right? Because at high temperature, we know we must get the Dulong-Petit law. Okay, so that is to say, at high temperature, we better get 3 nkb. Okay, so this is the first check. So check 1, high T limit. High T limit, what is the high T limit? High T limit, as usual, high temperature means you compare with the energy scale here, right? So high temperature, T is high, X is small. So high T limit means small x. Okay, so this means small x. Okay, so what can you do? You can expand this e to the x, right? And then just keep the leading order term for this integral. Okay, so well, it's not long. Let's do it. So you, in this case, your e to the x, you can expand it as 1 plus x. Right, leading order term we don't want anymore, and here you will see, you will get if you plug this in, you get x to the 5th. You don't want the second term, you just want the leading order term. Okay, and therefore x to the 4th, e to the x minus 1. This one will become x to the 4th, 1 plus x, and this will be 1 plus x minus 1, so there's x. And you have x squared. Okay. So I want to throw away this term anyway. It's, as I say, I just want the leading order term. So this will be x squared. Right. So the next term will be gone. Okay, and then you integrate this, and therefore the integral, this integral. I will call it C high, as is written here. Okay, high temperature limit will become 9 nkb T over d by cube times an integral 0, and then you have x cubed dx. Okay, and this is this whole thing is 1/3 of x cubed, and you evaluate that at d by temperature divided by T cube. Okay, good news. You this precisely cancel this, and this 1/3 cancel this 9. So you indeed get 3 nkb. So this is Dulong Petit. Very good news. If I don't get this, I will be in big trouble. So this is Dulong Petit again. Okay, now let's do the low T limit. The low T limit actually, let me see this slide. Okay, I don't want this. I want this, and do the low T limit. Okay, just pretend that this slide order is okay. Okay, low T limit. So this is, I wrote the check, right? Okay, this is 2 low T limit. Now this is easy. This is very easy. So low T limit, what do I have? This low T means temperature is much lower compared with the by temperature. So therefore, I can set in the low T limit, this ratio will go to infinity. Okay, so if I set this integral, the upper limit to infinity, then there's no T dependence here anymore, because this is a standard integral which you can look up at the table. So this becomes just some constant. Okay, so this becomes a constant. This is something you can find on some table, the table of integral. Okay, takes this value. Okay, and therefore all the temperature dependence are here. You have the T cube law you want. So here, in this case, this is some constant, a bunch of constant times T cube. Okay. Is it fine? So this whole thing becomes some numbers. This thing multiplied by this 9 nkb divided by theta, divided temperature cube. And therefore, you see, last lecture I showed you some data from my group. I show you the slope, right? At low temperature, you can look at C over T divided. You can look at the plot of C over T versus T square. You get this slope, and this slope is nothing but this guy. Okay, and the electronic contribution on that plot becomes the intercept. So from the slope of that curve graph, you can get this constant, and from which you can get your Debye temperature. Okay, and this is how people determine the Debye temperature. So you really need to go low enough to see this linear region in C over T versus T square for you to find the Debye temperature. Okay, so I gave you this table where you can see some Debye temperatures here. You can see it's of the order of several hundreds here. several hundreds Kelvin. So this is written in Kelvin. Okay, and one particular case is this. Now this is diamond. It says carbon, but this is really for diamond. A very, very high Debye temperature. Okay, so if you unify all these concepts, this again is consistent. You have very high Debye temperature, and therefore room temperature is not that low in this case, and that is why people discover the need of non-classical description for heat capacity. Okay. All right, so we are entering the final topic of the course, and that is about this Bose-Einstein condensation. So here we are talking about bosons that are massive. So we are going to talk about boson. So actually just call this massive boson, bosons with mass. Okay. So we cannot ignore the chemical potential anymore. We need to bring it back. And the idea is this: bosons are very friendly. They can you can put them in the same box. You can put many of them in the same box. So that gives some interesting idea. The idea is this: what about I take a collection of gas, a volume with that many gas particles, several thousands, several tens of thousands, and really put all of them together in the ground state. What happens there, and how do I achieve this? You can probably guess how to do this. The way to do this is to kind of place the centric, right? Reduce the temperature. Keep doing this, and keep cooling and cooling and cooling. And according to the picture we developed up to now, cooling will restrict the energy states that are accessible to these particles. At high temperature, they are everywhere. And then I just remove a lot of states by cooling. And therefore, they are kind of restricted to a smaller number of rooms, if you like. And I keep doing this until at some point, they are kind of restricted to a very small number of states, and then I do it again, and hopefully they are all going to occupy the same energy state. And that would be very interesting because they share the same quantum state, and you can think of these collections of particles as one giant atom. It's like one super atom, right? They are all in the same quantum state. Okay, so this is the kind of description I would develop in the last 40 minutes to 1 hour. Okay, so coming back to here, we cannot. So mu, you need to include mu again. So need to include mu again. Okay. And this is a massive particle with mass m. Okay, so the it's not very. Okay, this is the mass is m. This mass is so important because if you talk about different type of mass, if you want to explore this kind of physics, you will see the temperature scale is so different. If I have something very light, I can maybe hope to achieve this kind of condensate at higher temperature. If I have a very large mass, this temperature will need to go to a very low value. Okay, so in this case, here, we can use what we developed before. What is the energy spectrum? It's no longer linear, okay? It's not photon, it's not phonon, but we have this h bar square divided by 2m k squared, okay? And the ground state energy, just to remind you, the ground state energy is 0, is the ground state. And this is where we want to put all the particles. We would try to put all the particles, ground state. is the ground state energy. Okay, and what are these K? This K is depending on how you do your boundary condition. So for the periodic one, we will have nx times 2 pi over a, and then ky will be ny times 2 pi over a, etc. And the constraint will be on this n. So n can take this kind of value. Okay, so this is for periodic boundary condition. Okay, so this is already developed. And the distribution function is BE, Bose-Einstein. And I will just write the continuum limit right away. So I have n of epsilon d epsilon divided by g. Okay. And this you know how to write. This is 1 over exponential of epsilon minus mu kbt minus 1. Now, if you have done the last assignment properly, you know at this point you can discuss about this mu. And this is where we want to do it again, okay? I hope you have done this. So first, mu has to be negative. Okay, so mu has to be negative. Why? So mu, right? So this chemical potential mu has to be negative. Because otherwise, that is why I already stressed many times, this plus and minus 1 make the whole difference. You have this minus 1 here, which means you have the chance to actually accidentally hit a minus value here, and then you have this this ratio to be minus, which is not physical. Okay, so this is the number of states divided number of particles. This is the number of states. There's no reason why we need to use a minus sign to describe either of this. So there's no way that I want a minus sign here. Okay, so this minus here gives you a chance to get a negative value for this ratio, which you don't want. Okay, and therefore this explains why mu has to be negative. If you take the ground state, let's look at the ground state. Ground state is 0, right? So in order for this ratio to be positive, mu has to be negative, right? So minus mu is positive, and therefore this whole thing is greater than 1. This exponential is greater than 1, and the difference will be positive. Okay, so mu has to be negative. Why? The reason I already say. I will just, for your reference, I will just write, how should I write? Okay, otherwise, you get occupation number, occupation, one of these, occupation number would be negative. Let's say, let's just look at the ground state. For the ground state, so this is not physical. Okay. All right, so we need to discuss the sign of mu, and then we need to discuss the value of mu for this problem. Okay, if I want to have a BEC, what do I really want? Okay, let's start from 0 temperature. At 0 temperature, what do I want? Now, what I really want is I want all n bosons, all of them to be in the ground state. Okay, at slightly larger than t equals 0, I cannot say that. But at t equals 0, I want everybody to be in the same room, the ground state, the room for the ground state. Okay, and here we are looking at a large number. So this n is still large. Okay, this is the implicit assumption for this course, right? So all this n must be large for us to do statistics, for us to do a Stirling approximation. Now, if you want this to be large, mu better be negative but close to 0. Okay, at the ground state. So don't forget, ground state means this. Okay. And therefore, if you look at this expression, you know, if you want a huge number of particles in the ground state, which is to say, ground state is non-degenerate from here, right? Or you can let the degeneracy to be very small. Let's say this is of the order 1. Then this is really the number of particles, right? This will give you the number of particles. And this had better be a big number. Okay, so in order to achieve a big number for the ground state, epsilon equals 0. And the best way is to have this quantity to be close to diverging as much as possible. For this quantity to diverge, right? And therefore, this better be close to 1. So 1 minus 1, you will get a huge number of particles. Okay, so this is a way to look at this equation. Okay, so we want this, and therefore I will write again the key point for you. So mu has to be nearly 0, but still negative. So these 2 points are from this point, you know, this has to be still negative. Okay. Okay, my aim here is to give you the Bose temperature, which is the phase transition temperature for entering this state. Okay, so after I describe this, I will give you this expression, and this is the phase transition temperature. So you should keep in mind the goal of this treatment. Okay, let's. So the goal here is to get. So the goal is to give an expression of TB. Okay, this is the temperature above which you basically have everything is normal. And once you cool below TB, suddenly all these bosons becomes very, very friendly, and they all want to go to the ground state. Okay, so this is a phase transition into the Bose-Einstein condensate. Okay, so this still requires some a few lines of treatment. So we already discussed the 0 temperature limit, and now I want to discuss finite temperature limit, but I want to stay below the Bose temperature. Okay, so I want to discuss what happens when I raise the temperature a bit, but still all these particles are still have this desire to go to the ground state. Okay, so this is the threshold temperature, if you like. So the threshold temperature below which bosons, a macroscopic number of bosons, below which a large number of boson would go to the ground state. Okay, now here, I can give you the temperature dependence on mu. Okay, how do I do that? So the number of particle, if you look at this expression here, I'm going to just recast it into the number divided by degeneracy. Okay, so I'm going to assume the ground state is non-degenerate. So everybody goes to the same state. So I will have n naught divided by 1, right? The number of particles in the ground state, this is 0. This 0 labels the ground state, divided by g, but g is 1. And this is approximately given by 1 divided by this e to the epsilon minus mu divided by kBt minus 1. Okay, so this is the finite temperature. Okay, I put approximate. So this basically is nearly the entire particle numbers. Okay, you have n particles in the system, but I'm going to use this n naught to label them because I want to see the change. Okay, this point will become clear soon. But this is the number of boson in this state, in the ground state. Okay, so let's now the m here for these few lines is to work out the temperature dependence on mu. I know mu has to be close to 0, but how close? So let's have a look. So ground state, right? So I have e to the 0, right? Ground state minus mu kBt minus 1. Okay, so let me rearrange this like this. So I can write minus mu over kBt. So I would so how do I do it? Let me see. So I have this exponential. So I will take 1 over. I will take the reciprocal of this. So I have 1 over n naught here, and I have this minus 1 that I can move to the other side. So I have 1 minus n naught from the other side, and this minus 1 I can move to the other side, and that becomes plus 1. And then I have this exponential, which I will convert to log. Okay, so this is what I want. Okay, I will have a very large number of particles here. This is my assumption. Actually, so here, what we have is this n naught is very, very huge. So this n naught is huge. Okay, how do you define huge? So that is to say 1 divided by n naught is much smaller than 1. Okay, and then you can expand this guy and it becomes 1 over n naught. Okay, so I really have a lot of particles in the ground state, and that allows me to write down this line, and here I get the temperature dependence of mu. So that will be minus kBt divided by n naught. Okay. Now in the lecture note, I gave a slightly different treatment, but we will get the same result. So this is the temperature dependence of mu, and it also correctly gives you the minus sign, just like what I justified earlier. Okay. Now all this up to now should be quite okay, and in particular, if you have put in effort to think about the last assignment questions that you handed in 2 days ago, you might already manage to reach this result. Okay, now after this slide, what I'm going to say will be a bit more subtle. Okay. Really, I don't have a temperature dependence of mu to show you. Okay, wait a minute. Let me go to the next part first. So let me. Okay, now this subtle point is the following. Listen carefully. If I want to calculate n, the number of particles in the system, how do you do that? In your statistical mechanics treatment, you know, you write it like this. Right? You integrate the number. This is not number density. I'm sorry. The symbols have been the symbol might carry different meaning for different parts. So this is the number of particle occupying the epsilon state, and the continuum limit. You have this, and then you know how to write the next line. This is that. It's written like this. You have g of epsilon, d of epsilon, and then you have this function. Okay, so up to now it should be okay. All right, so the subtlety comes in now. What is this g of e? G of e, we already derived. So g of e, d of e is 4 pi m times volume v, and then you have this h cube 2m epsilon d epsilon. Okay, so just to remind you the origin, this one is coming from, this is equation 1010. Okay, and this expression is correct, has the same form, whether or not you use the traveling wave solution. Okay, so it's independent of the boundary condition we use. So let me just write like this: same form for both periodic boundary condition and the box boundary condition. Okay, and more importantly, there's one way to derive this, and this is the most intuitive way, is to derive it from this expression right away without going through the K space. Okay, we did this, we did all these different scenarios, and we arrived at the same result. So this is correct. But there's some bad news for boson here. Okay, so what is the bad news? Can you tell me the problem? Anyone? So bad news. Bad news should be given in red, right? Bad news. Bad news. Now the bad news indeed is this problem. Now this treatment give the density of states which is proportional to square root of E. Okay, so G of E is proportional to square root of E, the famous square root of E dependence. Okay, and therefore G of ground state is automatically 0. Okay, and that is really bad for BEC, because ground state is the one which we want to put many particles. Okay, and now look at here. If I really want to calculate this, I can adjust my my distribution function like what I discussed before, but I will not be able to account for the ground state because of this fact. Okay, so this G at 0 will kill the contribution from the ground state, even though you have a lot of particles there. So that is nonsense, because this n will exclude the contribution from the ground state. Okay, so ground state is excluded. Now this is really the artifact. If you do the summation, you won't have this problem. When you convert from summation to integral, this is where the problem comes in. Okay, so we have to fix this first. How do we fix this? I'm going to call this. Look at the screen carefully. I don't want to copy again. Okay, so because of this, I cannot discuss the ground state, but this is the only problem. This is the only state I cannot discuss. Okay, so I should think about this as, now if I rewrite this integral as integrating from slightly above 0 to infinity, I will get the same result. Before we didn't care, because let's say you take Fermi gas as an example. These two will have a very tiny difference, so tiny that you won't care, because you are in the large n limit anyway. But now you cannot you cannot really ignore that. Okay, so when you do this integral, what you are really doing is this integral. Okay, so for the case of BEC, I have to call this the excited state, and then treat the ground state separately. Okay, so let me say this again. You count the total number of particles, total number of boson in the system using this formula, but the density of states formula exclude the ground state. So what you are really doing is actually integrating from slightly above epsilon equals 0 to infinity. Okay, and therefore in the case of BEC, you should regard this formula as a machine for you to search for all bosons not in the ground state, and therefore those are called the excited state. Okay, and once you realize this, things will be better. Then you can continue. Okay, so I will call this n excited, and therefore n excited is related to n naught, right? This n naught is the particles, the number of bosons in the ground state. So these two should sum to the total number, right? And therefore this is the difference between the total number and those bosons in the ground state. Okay, cool. All right, so now we just have to discuss what happens with the with this NEX with the appropriate chemical potential. Okay, so this expression, two expression, I need to write two expression for you, but I will write it carefully here. So n of the excited state. If I copy down this one, you will see this is a general case for pi mv h cube 2m, and then I have this square root of e dE. Okay, so this is true for all temperature. So this is for all temperature, right? If I know how to write my mu, this is true for all temperature. Okay, the spatial case is below the phase transition, below TB. So below TB, I will have this whole thing again. Right, I already know how to calculate this. So this will be 4 pi mv h cube 2m and then I have this. And I have e to the epsilon divided by kbt minus 1 because I know, so this is, sorry, this is for T below TB, low temperature, okay? And I can do that because mu is approximately 0 here. In order to suddenly have a lot of particles here. So maybe I should write it like this. You should understand that this is this mu is not exactly 0, but close enough to 0 compared with other quantities. Okay, now this is finite temperature, and we can look at this. So this will be the number of bosons. They are not in the ground state. Okay, so what we need to do is to continue with this treatment here and try to get the phase transition temperature. Okay, so this will take a little bit of time, a few lines. So maybe let's take a really quick break, shall we? Just 3 minutes, and then we will continue and finish off this course. Okay? So come back at 1:35. Thank you. Okay, welcome back, and let's continue. So I need this slide. Okay, I want to continue from here and manipulate this expression a bit more. And this is the same old trick again. You have seen it before. So I'm going to let x to be this ratio, hoping that I can rearrange it in the form that I can integrate and I can have an integral of a standard form for me to find the value on the integral on the table. Okay, so remember, you need to then do this d epsilon again. Okay, so if you do that, you will find this result. You find v 2 square root of pi. This is a 2. And then you have a bunch of factor here. And then you have this 0 to infinity, square root of x, ex minus 1. Okay, now I didn't do it for you, but you can kind of see this must be the correct form, right? You have this x here, and then you have this d epsilon, so you must have dx, sorry, and then you have this square root of epsilon here. Okay, now this integral has this value here. So this is 2.612 square root of pi divided by 2. Okay, so this is coming from this expression, okay, this second expression. So let me bullet point it for you. So this is from here you can write this form, but if you are below TB, you can let this to be 0. Okay, so this belong to this. Okay, so your n sub ex, the number of bosons in the excited states, will have this very famous form, 2n pi kbt divided by h squared. Right, so right now is really just playing with the equation. So this get pulled out here. So 2 over pi, so 2 over square root of pi, and square root of pi divided by 2. So this cancel. Yes, so this is correct. Okay, so let me mark it for you. This is to remind you, this is t divided by TB, but this is not enough. We want something. We want to find TB next. Okay, so this is equation. So how should I mark it for? I'm going to use dollar sign now. So this is $1 or $1. Okay, this equation I will need later. Okay, by definition, what is TB? Now, TB is defined as the temperature above which all bosons are in the excited state, right? So at TB, above TB, things should be normal. You shouldn't have such a huge number of particles in the ground state. So if you look at the entire spectrum, energy spectrum, you would actually expect instead most particles are in the excited state and not that many or even very tiny amount, 0 of them or approximately 0 boson would be in the ground state above the phase transition. This is something you would expect. Okay, so let's define. This gives you a definition of TB, because you can then say this something like this. So at TB, at T equal TB, I would expect right at this moment, the total number of particles can be regarded as the number of particles in the excited state. Where do I find all these bosons? They are all in the excited state. So this is this gives me the way to define TB. Okay, so I let the TB, so I set this NEX to be N, which is a system parameter, right? So I can get this equation. N is 2.612 times V multiplied by this whole thing divided by H square, H square multiplied by TB. So this is according to my description. Okay, and if I rearrange, I will get TB, the expression for TB. So this TB is H squared divided by a whole bunch of constant 2 pi KB times M. This is important. I already hinted that the mass is important. So you can see the mass enters now. And then I have this density, which is also important. Right? This is number density. Okay, so let's box this one. Okay, and then I will need this expression. This is $2. Okay, you can see that the how to get from equation $1 to $2, and this allows you to find the phase transition temperature. Okay, so just a recap for 0 temperature. We expect almost all the boson to be in the ground state. So I can make some statement now. So the recap, this is the picture you should have. At 0 temperature, precisely at 0 temperature, I would expect all N bosons to be in the ground state. So I will have this result. Okay. And when I'm at the temperature above TB, I would expect the opposite. I would expect to be able to find all of them in the excited states. Okay, and now the question is, how do I what happens between 0 and the phase transition temperature? Okay, and this is actually this figure here, right? What I just say, this is plotted as ratio. Okay, as I say, at the 0 temperature limit, I should expect this n naught divided by n to be 1, right? So this line here shows you the temperature dependence of n naught. So n is a system parameter, so n is fixed. Okay, so the n boson will not be in the ground state at all above the phase transition temperature. Okay, it's approximately 0. Instead, they should all be in the excited states. And you cool down, and once you hit the Bose temperature, these bosons in the excited state suddenly become very interested in the ground state, and they will start to escape and go to the ground state. And that's why you see this drop for the excited states particle, and then you see this rise for the ground state bosons in the ground state. Okay, now this is schematic, but we can actually plot it. We can actually give you something more concrete than that. So you just need to see this part, right? This temperature dependence. Here you can use this. You can use words. You can just justify that we should find all the bosons in the excited state. So this is a horizontal line, no problem. Okay, but how do you get this curvature, and how fast does it decay? Because this is related to how we calculate the heat capacity. Okay, so let's first get this expression here. We know N naught is N naught plus NEX is N. So N naught is N divided by NEX. Okay, we want to reconstruct this figure, so I will divide by N. So I get this expression. That's to say, once I get one, I get the other one. Basically, at any point when you read these two values, they should add up to 1. Okay, so when things happen, they should all conserve the particle number. That is why we have this full expression for Bose-Einstein distribution. Okay, so this the interpretation is very straightforward. This is the fractional number of particle in the excited state. And how do I get this expression? I will use, now I'm going to flip back to this slide. I'm going to take these two expressions, right? Because you see, I want NEX divided by N. Once I know one, I know the other one, because they are different by 1, right? So I have NEX divided by N. So I have to use this expression and I divide by this expression. Okay, and everything just disappears. You see, everything disappears and you get your temperature dependence. Okay, so if you do it that way, you will get T divided by TB raised to the power of 3/2 for NEX divided by N. Okay, so this I don't want to write too much. So I want the ratio of NEX to N. So I take this expression, divide by this expression. Everything else is the same except this factor T and this factor TB. And don't forget this exponent of 3/2. Okay, so look at this, and then I come back here. I can write 1 minus this ratio will be T divided by TB, 3/2. Okay, and this is the temperature dependence of N. Sorry, this is the temperature dependence of N naught. Okay, so this tells you how fast it grows. Okay, so this is this form here. Okay, so this is implicit. We want T to be in this range, right? Above that, you will begin to get again non-physical value, because this will be greater than 1, and then you will have trouble. Okay, so this is the picture you should keep in mind when you try to understand what's going on with BEC. Right? Up here, it almost appears that the system has no interest in the ground state at all, and suddenly, maybe you can imagine maybe there's some spatial attraction in the ground state, and they all want to go there. And this is what we always call the macroscopic number, even though this grows from 0, but this is a huge number of particles. Okay. And next, we need to get this form. But before that, I think, let me check my note. I think in my note, there should be the temperature dependence on mu, and you should have a look. Doesn't matter, I will plot it for you. So this mu as a function of t, and this is TB. It will be very small, very negative but small. And then it should grow like this, but still negative. Okay, so this is something you can look up my note, and hopefully, if I don't put it, I will include it later. Okay. Okay, heat capacity. How do we do this heat capacity? Heat capacity, first we have the recipe, right? We always start from internal energy. So the internal energy U is just like what we found before. Okay, so this internal energy U, now I'm going to write the sum for you. So we will have this form right from the beginning, right? We know how many particles in the ground state, how many particles in K equals 2, K equals 3 states, and then we work out the energy value and take the product. Okay, and now because for BEC, ground state is so spatial, so I'm going to decouple this out. I'm going to rewrite like this. I'm going to rewrite, sorry, K, non-zero K. Okay, so the ground state contribution and the high K contribution. So this is the ground state. Okay, and now just follow me closely. Okay, again, I don't want to keep rewriting things. Now here, this N, we have a different symbol. We use capital N, so they carry the same meaning. Okay, so this is the meaning. This is the meaning of internal energy. But look, if you look at this expression, you will see that the first term will not contribute to the internal energy in any case. Because if you are in the ground state, epsilon is 0. So this term is gone. And if you are above the TB, there is no particle in the ground state, or very little particle in the ground state. They do not add anyway. Okay, so in any case, because of the fact that you single out this, you do not expect the ground state to contribute to the internal energy, and therefore it also does not contribute to the heat capacity. Okay, and now I can play the same trick again and do this hand waving argument. So the hand waving argument is I will look at how many particles are in the excited state, and then assume each one of them take the thermal energy of kBT, and that will be my internal energy. So I can estimate. So so after this argument, I won't write it down. Okay, so U can be estimated based on based solely on NEX. Okay, so how do I do that? I take this to be roughly the number of particles in the excited state. And then where do I find them? Most likely I will find them not too far away from the thermal energy I give to the system. Okay, now because there's a distribution, this kind of treatment cannot get the prefactor right, just like in the case before. But one thing we can do is to get the exponent right. Okay, so if you plug in this NEX here, NEX is N times this factor here, right? So you see NEX is written here. Okay, so NEX is N times T divided by TB, 3/2, and multiply by KBT. Okay, so the point is, this is how you estimate this temperature dependence. So this is proportional to T to the 5/2. So this is T to the 5/2. So just to remind you, this is in this temperature range. So let me write this down. Okay, so the hand waving argument can tell you this temperature dependence, but it cannot get the prefactor right. And if you do the more proper treatment, the integration, you will get the prefactor of 0.707, 0.770 in front here. And that is the prefactor you want. Okay, so sorry. This is the internal energy. So you cannot get the prefactor right. And therefore, if you do the du dt to get the heat capacity, you also cannot get the prefactor right, but you can get the T dependence right. Okay, so if you do this, CV, and if you do the full treatment, you get the prefactor right. Then you take the derivative to get the heat capacity, you get 1.92 times NKB times T divided by TB. And now, because you take the derivative, this power has to be reduced, so you get 3/2. Okay, again, this is for T between 0 and TB. Okay, so suppose you go and measure the heat capacity. You should get something like this at the low temperature. Okay, and 2 points I want to discuss. What's this? What's the next? Okay, this is actually a very realistic plot. This is the phase transition temperature. So if your heat capacity grow from 0, and if you set T to be 0, so this is full treatment. So sorry, let me make more notes for you. So this is estimated here. So this is full treatment, which means you take the integration seriously, and then you get this prefactor. Okay, so if you put this prefactor, you will see it will grow from 0. Heat capacity will grow from 0. So this is CV normalized to N times KB. Okay, it will grow from 0, and then it will shoot up, and right at TB, you will get 1.92. Okay, so this value is 1.92. Okay, and then above here, this temperature dependence is hard to calculate, but you should expect to get the limiting case. What is the limiting case? If you keep going up in temperature, eventually you should recover the classical result. So this whole thing will approach the limit of 3/2 NKB, right? And that is to say, if you, I don't like this plot. So here, if you go to the limiting case here, so this line here should be 3/2, which is 1.5. Okay, so this value is 1.5, and this peak value, the horizon, the peak takes the value of 1.9 on this scale. Okay, so if you're at TB, your heat capacity is higher than the high temperature limit, there must be a peak. So this is how we construct the argument. You can actually do more. You can try to calculate. It's not necessarily easy. You can find the temperature dependence, but limiting case is clear. When you approach TB, you should take 1.9. When you approach high temperature, you should get 1.5. So there must be a peak. Okay. Now the question for you. So this is a classical limit. This is classical limit. Okay. Is it a first order transition or not? So at TB, this shows you there's something is happening here from the heat capacity. This is how we use this tool to diagnose whether a system is going through a phase transition. Okay, so this is, which order do we have here? Okay, I guess some answer. Oh, good. More? And more? Now, this is just assume this picture I give you is indeed what I want you to look at. Although I don't present the detail, but okay, just assume this is the correct form. My question for you is, if you look at this temperature dependence of heat capacity, and using your knowledge from phase transition chapter, how do you classify this phase transition? Good, I get one correct answer. This is the third order phase transition. Why is it not a second order? Because in the second order phase transition, I should expect a jump in the heat capacity. I should expect the first order derivative of the free and of the energy function to be continuous, but it shows a kink. Okay, then the first order derivative in that case is entropy. So if entropy is continuous but shows a kink, then the next order derivative will show a jump, and the next order derivative will be heat capacity. And if the heat capacity shows a jump, discontinuity, and this is a second order phase transition. But now, the discontinuity will happen when you take the next order. Okay, so this is a bit like this is continuous, but non-differentiable here. Okay, so this is this heat capacity tells you this is a third order phase transition. Okay, good. I think if you have read my notes, then you will get this answer. If you haven't and you analyze it yourself, then this is very good. I'm very happy to know to learn that you get this correctly. Okay, now where do we find that? Where do we find this physics? So I would like to invite you to look at this again, to look at this equation again. Okay, if you take helium-4 and plug in the density, right? You can look up the table and find the density. This is basically the density, right? The number of helium particle per unit volume. This tells you the density, and you know the mass of helium-4. I keep saying helium-4 because helium-3, the isotope, is a fermion. Helium-4 is a boson. And the excitement is this. Just shortly after the this theory about Bose-Einstein condensation, you know, is predicted a long time ago. by Bose and Einstein. They discovered this. And not long after that, there's another discovery in helium-4. And if you, let me continue. If you do what I say, plug in all these numbers, you will find for helium-4, you need the mass, you need the density. For helium-4, you can calculate TB to be about 3 Kelvin. Okay, so this is not too bad. So the precise number I don't remember. Let me see. Okay, I think it's about 3.1. Not too bad. My memory is quite serving me quite well, but around 3 Kelvin. Okay, and in helium, there's this phase transition, which is at 2.2 Kelvin. This is called the lambda transition, 2.2 Kelvin. Okay, so that generated a lot of excitement because it's natural for people back then to relate these two phenomena. Okay, so this is not too bad, 3.1 Kelvin and 2.2 Kelvin. But the problem here is first, if you look at the shape of this transition, it's not quite the same as what I gave you earlier. And then the other more serious problem is this. In helium, it's not appropriate to assume non-interacting system, whereas everything we have treated so far is non-interacting. Okay, here in helium, this is liquid helium, by the way. So this is liquid helium. This interaction is actually very strong. And therefore, this cannot be a complete description. Okay, this turns out to be a superfluid transition, right? So you have liquid helium, and then you enter the superfluid phase at T lambda. Okay, and it was exciting because superfluid is also some kind of a coherent phenomena. So you assume all this boson goes into the same ground state and then act like a coherent superatom. And it can flow without any viscosity. But from here, you know, this is not the full story because the non-interacting picture we have discussed so far might not be that appropriate. So although this has been discovered long ago, it wasn't regarded as the conclusive proof that the Bose-Einstein condensation truly exists. So for a long time, it was regarded as a mystery, a toy, a theoretical toy, which needed to be confirmed. Okay, and this is a famous picture. When do we get this final approval stamp from the community? And this comes from the experiment at about 1990s, mid-1990s, 1995. This was done using a very, very dilute gas of atoms. Okay, so here is a Nobel Prize winning work. And the Nobel Prize was awarded in 2001 for cooling down rubidium 87 atoms. So rubidium 87. So this is 2,000 particles, 2,000 atoms. And then the other one, almost at the same period, is cooling down sodium atoms. And here is of the order of 100,000 atoms. Okay, and the density, if you look at the density, here I cannot tell you the density without telling you the volume, but I will quote the density. The density is about 10 to the 11 to 10 to the 15 per centimeter cube. And from the equation for TB I gave you, you can plug in these numbers and you will instantly discover, wow, this is crazy. How did they manage to do this? What is the temperature to realize this kind of physics? And you realize once you plug in the number, TB is of the order of nanokelvin for rubidium and a bit higher for sodium. So the experimental temperature, let me quote the experimental temperature, where they begin to see condensation is 2 microkelvin. This is very, very tiny, and 170 nanokelvin for the rubidium experiment. Okay, and this led to another Nobel Prize, because to really cool down to this kind of temperature, you need a lot of smart ideas. Right? How do you do laser cooling, and how do you use some trick to get rid of some particles that are very hot, and then you trap those that are colder to make your experiment more possible. Okay, and this is another Nobel Prize. So from here, this is the famous picture you see. Now, kind of think about this as some kind of a velocity map, some kind of 2D velocity. Okay. Now, in order to plot it in 3D, we have to show it like this, and the vertical will be some kind of number. Okay. Now, just suppose you know how to measure the velocity of the particles, and then you know how to do statistics. Okay, so this is above the phase transition temperature. So from here to here, this is T higher than the phase transition temperature, and this is T just below the phase transition temperature, and this is much lower than the phase transition temperature. And you really see the picture I gave you, right? You really see the particle begin to want to go to the ground state. Okay, above that, just above that, you already see there are some particle going to the center of this graph. Okay, so just imagine this to be proportional to k, right? I actually don't need to imagine, this is indeed the case. So the velocity is proportional to k, right? mvx is h bar kx. So this is proportional to k. And therefore the ground state will correspond to 0 k's, right? Kx equals 0, ky equals 0. And you begin to see the build up of this peak here. Okay, that is to say that you begin to get more and more particles who will want to occupy the low energy state. Okay, so this is you might say, wow, this is a broad peak. True, this observation is right, but then you should also appreciate the fact that at the zero temperature, at the center of this, where you have the ground state, you do have a sharp, you do have a large number of particles there. Okay, so this kind of prove the existence of BEC, and therefore it proved that this statistics developed by Bose and Einstein was correct. Okay, so this is the last slide, and I will conclude now. So I will show my PowerPoint. Okay, so just wait a minute. Let me switch to a different. Okay, can you see the screen? No, it's sharing with you. No, sorry. No. Okay. Sorry. Here. Now? Yes? Okay, I'm going to switch to full screen. If you cannot see, you need to shout. Can you see? Okay, so I'm going to conclude this course now. So first, this is a chapter summary. This is everything we discussed today, actually 3 and 4, these 2 items. Okay, so as I promised, if you want to learn BEC, superconductivity and superfluidity together in a coherent way, there's a nice book here. And this is the book by Annette. Okay, and then when you study this, the unifying theme, if you like, for this book is the so-called macroscopic quantum coherence. Okay, this super atom business I talked about. Okay, and another thing maybe for you is to realize that actually here we have active research groups working on BEC and my group working on superconductivity. Okay, so I will talk about mine just in a few minutes. So I will just tell you what we are working on here. So basically, what we are interested is how to control the property of the superconductor. Another way to look at this is how do I find superconductivity? Where do I find superconductivity? So you can kind of appreciate this because there's no known theory for you to find superconductor. There's no way for people to tell you, okay, you mix this compound, this element, and then you cook it at this temperature, and you cool it down, you have a superconductor. Unfortunately, at this moment, there's no theory like this. So what we can only do is to come up with some recipe to find things. This is a bit similar to how the question of how to find life outside our planet. You can have some rule. You can say, okay, I need to have water, I need to have oxygen, I need to have this element. So these are all called guiding principle. You cannot guarantee life to be found once you satisfy all these requirements. So we need to play with this kind of guiding principle. Okay, so our guiding principle is we work on the phase transition. We look at the pictures, some phase diagrams constructed for other superconductors and try to learn from there. And you will see, for example, this is a superconducting region. This is the temperature. This is some parameter that we can control. And you can see near this phase of interest, there's a huge insulating phase, anti-ferromagnetic insulating phase. Okay, and here as well, you have some, this SDW is called spin density wave, is some kind of magnetic phase. And the superconducting phase is here. So if you look at these diagrams, you can kind of appreciate something else, right? You can say, these are the recipe for finding superconductors. It doesn't guarantee you superconductivity, but you can try. That is to say, you take a magnet and try to suppress the phase transition temperature. You take a magnet here and try to suppress the phase transition temperature. And when the phase transition temperature is sufficiently low, you look carefully around that region and hope for the best. Okay, so this is one punchline you can use to understand these phase diagrams. Okay, so these are some CUHK results, and you can see again, this is some interplay between a different phase. This is a structural phase transition and superconductivity. So this is a superconducting phase. So once you adopt the same strategy, you can optimize the superconducting property here. Okay, and here this is another one. You have a double helical magnetic state. You can imagine the spins kind of rotate around in space, a bit like DNA. You have this helical structure, and you try to kill it. And interestingly, you also see superconductivity. So this is the orange. The yellow region. Okay, so my group used pressure, which is something important for this course, right? We talk about PVT system all the time. So we use diamond and then put material in the middle, apply pressure, and that allows us to travel along this axis here. Okay, just like other people traveling horizontally along this axis. Okay, another thing, this is recent work with Professor Yangson's group, and we use diamond to do experiment, but at the same time, diamond can be functionalized as a detector, as a sensor. So if you have nitrogen vacancy in diamond, this is a very powerful sensor for us to send superconductivity. So you can, this is how we detect the Meissner effect, which is a signature of superconducting phase transition. In addition to that, we are also very interested in probing the metallic state, the unusual metallic states, because there you have all these fermions, and all these fermions will give rise to Fermi surfaces, as you learn from this course. And most likely, in most of the cases, these Fermi surfaces are not spherical. If they are spherical, I have to close my lab. There's nothing much to do. Okay, interestingly and luckily, they take all kinds of shape, and understanding the shape, the size, will be important for us to understand the metallic state. And if the metallic state is the precursor to the superconducting state, so naturally we want to understand the metallic state first. So this is, you already saw this picture before, and this is coming from my former PhD student, Miss Hu, and she did very beautiful work. And another message for you is what you learned in this course, this Fermi surfaces, although it's spherical, it can, in real material, it might not be spherical. And importantly, this can be measured experimentally. Okay, and we are also interested in the unusual normal state. For example, here, the resistance becomes very large in magnetic field. This is a magnetic field, and this is resistance proportional to the resistance. This picture is the clearest. You apply magnetic field, you can kill superconductivity. Fine, this is, we already know. But then if you increase the magnetic field, the resistance increase linearly, and this is something we don't, that came as a surprise. Okay, so if there's any interest in this kind of research project, you can contact me or other groups. There are groups here working on things that are relevant to this course. Okay, so to conclude, I want to show you this slide, which I gave you at the beginning of this lecture 4 months ago. And in this slide, I promised to discuss this, and happily, I have discussed everything here, plus the non-PV system, plus the open system. Okay, so we have achieved all this. So this should be crossed, and these are the topics we have discussed. Okay, so finally, let me show you the announcement again. And these are the points you should really pay attention. And if you are still with me, please look at the screen. This is very important point. Okay, the coverage of the exam would be from lecture 1 to the final lecture, except Bose-Einstein condensation. So this is my final gift to you. Okay, thank you very much. And now, if you have questions, we can discuss. So this is the end of this course. Okay, let me plug in. So 1341. Let me pick this up again. Sorry, let me set up again and go back to. Do you see any share screen now? No, maybe no. Okay, still the thank you page, huh? So I want to go back to bit paper. Okay, yes. 1341. Okay, here you are right. Actually, we don't. Here, the ground state is 0. So you're right. So even if we don't have whether we have particle or don't have particle, it doesn't matter. But if you have a lot of particle, you might expect this to contribute to the heat capacity or the internal energy. But the point here is the ground state is 0, so I can revise this. What I wanted to say, I think, is the following. Even if you have a lot of particles in the ground state, they do not contribute, which is a point that some students might not appreciate. Okay, and finally, if you have revision request, for example, if my note is not clear, you can ask me to revise. So the next question is, may I ask, is the chemical potential dependence of T found by experiment first or what? That I don't know which one is first. Sorry, this I have no clue. Why does it bother you? Which one first? Wait a minute. Let me. Oh, about this figure I drew by hand. This figure I drew by hand, right? Wow, this for me is seems natural. Now this argument of chemical potential to be negative and 0, this is something you can appreciate, right? Negative but close to 0, because you suddenly have a lot of particles coming in. So this is coming from this expression I gave about this n. So you can actually try to calculate this by putting some n. I put the approximation. I assume this to be a large number. Where is it? Right, this one here. Right, so I assume this to be a large number, but you see what we compare, what we really compare is this +1 here. Okay, so if you really want to find out the true dependence, you can calculate this quite accurately. And then above that, that will be how do you do this experiment? I don't quite know right now. Right, so everything is this chemical potential is in. For you to do this adjustment such that you get the total number of particles correctly, right? This total number of particle n has to be accounted for once you do all this integration. Okay, so I think now which one is first? Naturally I would say theory is first, because of the difficulty to create this kind of particle. But how do you measure this directly? This is something I'm not too sure about this system. Recently, I read 2 articles. Last month, I read 2 articles. And it's about measuring the chemical potential of a different system. And interestingly, the way they do this measurement is now chemical potential for that system, it's hard to measure. Okay, it's some kind of thin film, carbon-based or graphene-based thin film, and they put one sentence which I would think you will appreciate a lot, because they say, this is something which is very difficult to measure, this chemical potential. Let's do some thermodynamics and convert this using Maxwell relation into an expression that is experimentally accessible. So I will guess, guessing for such a system, maybe a similar logic can be adopted. Okay, and then the next question is BEC will not be included in the final. So it's about half of chapter 13. So you should, now, it's up to here. One is photons. If you read chapter 13, I don't know whether it's half, but just before session 3. Okay, but it's not the same as saying that the Bose-Einstein distribution is not going to be the exam. Okay, the two quantum statistics are examinable. Now, there are many people here. I think I'm still recording. So this is not tips just for you. So this is what I'm saying to those who care to watch this video. Okay, now I'm going to stop the recording. And any more question about the exam? So let's start from this. Okay, and Harry, you asked me to check 1340. I will do later. Okay. Okay, if there's no question, I will say goodbye to you here and now. Okay.